start recording. Yeah, I am personally recording for my YouTube, and then Res is also recording. I think this is being recorded. Yeah, I think it is. I can't see the recording button, but probably you see on the screen somewhere the recording. But anyways, I'm recording it, so it'll be posted on my YouTube, so you can access that. It's just my name. It's just Adam Sala. YouTube. YouTube is just my name here. And also, as always, it's being recorded by Zoom as well. Good. So it'll probably be emailed to you, just to everybody. Also, of course, you can access my notes for this course, which are fully up to date. I hope they are up to date. Yes, at tutor.ca/notes. Okay, and you can see all of my notes for all of the courses that I'm taking, except CMN, which I don't really take notes for. But yeah, every other course, there's some notes for it, especially all the engineering courses. So yeah, feel free to access those. Those are for free. Okay, so let's just begin with some of the practice problems I have here. So yeah, let me just start here. Here's a bunch of just kind of like fill in the blank questions, which are pretty good from the Susanna Epp textbook, right? Just to, really hopefully understand what a relation is. So a relation R, so if R is a relation from A to B, X is in A, Y is in B, the notation X, R, Y means that, well, what that means is that the point X, Y is an element of R, right? So an R itself, the relation is just a set, right? So that should go in there, but I can't fit it, right? R is just a set. It's a set which is a subset of A cross B, right? So what that means is just like fancy words to say R is a bunch of ordered pairs, right? Order, so order matters, right? Just because X, R, Y doesn't necessarily mean Y, R, X. So you have a bunch of ordered pairs, and they are combined. You're essentially ordering one element from A and then one element from B. And they don't have to necessarily be the same set. Now, a lot of the time we think about, a relation on A, meaning from A to A, but it doesn't have to be that. There's no reason for it to be that. Okay, that's just a special case. So everybody stop me if you have any questions, obviously, at any point. So if R is a relation from A to B, X is in A, Y is in B, the notation X not related to Y means that X, Y, obviously, is not an element of R. That's all it is. If R is a relation from A to B, X is in A, Y is in B, then Y, X is an element of R inverse. If and only if X, Y is an element of R, right? Because R inverse is the inverse relation, which takes all the elements from B and puts them back to A, right? So Y and X, right? So here you need X and Y, and that's an element of R. Doesn't R also need to be a one-to-one function for this here? Well, you can have an inverse relation, and you could have, so the thing is, like, if you want to call it a function, if you want to call this inverse relation a function, then yes. But we don't necessarily want to call this inverse, like R inverse. We don't necessarily need that to be a function. It's just a relation, right? Yeah, there you go. Good question, though. So a relation on a set A, R inverse can point to two preimages. Yes, it can. Yes, right. A relation on a set A is a relation from A to A. That's all it is. It's just, understanding what a relation on a set is just a subset of A cross A. That's all it is. If R is a relation on a set A, the directed graph of R has an arrow from X to Y if and only if X, R, Y. That's all it is. So when we take a relation and we draw a directed graph, right, which is just a graph that has, it's not like, going from A to B, node A to node B is different than going from node B to node A, right? Then we just draw a directed graph. And we draw that if these two elements are related, and the order matters in a lot of cases. Okay, guys, let's try this example here, okay, which is about just basically asking, we have some sort of relation on X, on some set X, which is the set ABC. So let me just read the question. And we just want to see if things are related, but it's a little bit complicated because you have a, a power set. Can everybody hear me properly? Because the Zoom microphone level is like 1 pixel for most of the time. I wonder if it's something with my microphone or something. Can everybody hear me nicely? Yeah, you can hear fine? Okay, sounds good. It's just weird that it's just 1 pixel. I don't know. Yeah. Video's a bit buggy. Like, my writing is a bit buggy. Or the actual camera. Just the camera, but the writing's okay? Writing's okay? Okay, if the writing's okay, then whatever. Yeah, whatever. So let X be ABC, the set containing A, B, and C. Recall that the power set of X is the power set of X, define a relation R on the power set of X as follows. Right? So for all sets A and sets B, which are elements of the power set of X, ARB means that A has the same number of elements as B. So let's just take a look here and see, which ones of these are true, right? So first of all, we just want to make sure that these are both elements of the power set, right? So they are elements of the power set, right? Because the power set of X is equal to the set which contains the null set, the set which contains A. I just immediately have to forgive my brackets. I'm not going to carefully write them. A, B, C, the set which contains AB, the set which contains AC, the set which contains AC, and finally the set which contains A, B, C, right? There. So that's the power set. We just want to make sure both these elements are in the power set, and they are. And now, if they are related, that means they have the same number of elements, right? So this set has 2 elements, and this set has 2 elements, so this is true. This is a true statement, right? This would be a true statement as well, because this is an element of the power set, this is an element of the power set, and they both have the same number of elements, and then this would be false. Right? So true, false, true. That's what it is. Okay. There's that example. If there's any questions, let me know. But that's it. That's really all. So now let's get into, I lost one of the things that I want to write. Here it is. Yeah, okay. Okay, let's get into, okay, I see the order I'm going to do it. Get into this. For each of these questions, for 14 and 15 here, by the way, all these questions so far are from the other textbook, the Susanna F textbook. Just I cut out the question, but it just says draw a graph representing the following. So we just want to draw a graph for each of the following relations. So for 14, right, we want to draw a graph that uses illustrates this relation. So define a relation S on B. So it's a subset of B cross B, right? By S is the relation. So A is related to B, A is related to C, B is related to C, D is related to D. So let's go ahead and do this. So A, B, C, and D are all elements of the A, B, C, and D are all elements of this relation, are all nodes of the graph. And now we just draw a line, a directed graph, right? Connecting to, I guess I should say, draw a digraph. Connecting to if they are related. So A is related to B, right? A is related to C, right? B is related to C, and D is related to D. Right? Nothing's related to D except itself. Okay, and there we go. This is a graph that represents this relation here. And we'll talk a little bit about this, if this is transitive, reflexive, symmetric, in a second. But for now, let's just draw the other graph here too, right? So the other graph here is we have a set A, right, which is 2, 3, 4, 5, 6, 7, 8. And we want to define a relation R as, X, R, Y means X divides Y, right? So, like 2 divides 4 is true, right? Because 4 can be divided by 2. So let's draw all the elements here, 2, 3, how should I draw it? I guess 2, 3, 4, 5, 6, 7, 8. That's how I'll draw it, I guess. And now what divides what? Oh, actually, I have to label all the points. So 2, 3, 4, 5, 6, 7, 8. So, like I said, 2 divides 4, right? 2 divides 4, yep. 3 divides 6. 2 divides 8. Anything else I'm missing? 4 divides 8. And that's it, I think. Unless I'm missing something. Nope. Oh, 2 divides 6. 2 divides 6. 2 divides 6. Yep, that should be it. That's everything. 2 divides 2. Yes, that's true, actually. That's true, actually. Yeah, everything divides itself. Right? Everything divides itself. That is important. Okay, that is an important one. Everything divides itself. And that's it. There we go. That should be everything. so there is our digraph for this relation here. So any questions about this, how I drew this graph here? It's fine. Okay, so it's 15. I don't know why. What's the graph on the left? Yeah, that's for 14. And I don't know, I labeled them both 14 for some reason. There we go. Yeah, 14, and this is 15. So let's ask ourselves, if this is transitive, symmetric, and reflexive, right? So first of all, reflexive means, let me get the definition like how I wrote it. I won't write it here, but I'll just put it like this. So there it is. So it's on my website, obviously. Oh, for some reason it says couldn't preview file. That's weird. Okay, something's wrong. Can anybody else access my notes? I'll find it. It's okay, I have the actual copy on my computer, but just strange. Okay, so the definition of reflexive, no, that's fine. Now it's partial orders. There we go. It should be here. There we go. So reflexive means, I'll just write this. There is our nice little box of all the different binary relation properties, right? So reflexive means if for all A in A, right, A are A, right? So let's just take a look at both these. So is this reflexive? What do you think? What do you guys think? This one here, is this one reflexive? No, right? This is not reflexive. So not reflexive. Is this one reflexive? Hannah, you got this one? What do you think? Yeah, it's reflexive, right? So is reflexive. Okay, good. Yep, that's right. Because everything's related to itself. Every element is related to itself here, right? So here we could make this reflexive by, adding these relations, right? And now it's reflexive. But without that, it's not reflexive. So no. Okay, then symmetric, right? So if A is related to B, then B is related to A, right? So, either of these, what do you guys think? Are either of these symmetric? No, it's not symmetric. Both no, right? Not symmetric. Just not symmetric. Not symmetric. Right? Yeah, that's right. And so now transitive. What do you think about transitive? 14 is not transitive, but 15 is. Yeah, let's take a look. I don't know, right, just by looking at it. So transitive would mean that I have some sort of connection. So for example, if A is related to B and B is related to C, then A should be related to C, which is true. We have that. Let's see if we can come up with any other things here. If A is related to C, C is related to nothing, right? So nothing, that kind of ends there. So we don't really have a link. The only link we have is this and this. And so I think this is transitive. I think this one is transitive. Unless I'm missing something. D is related to D, right? So this one is transitive. So you just kind of want to make these kind of links. It's really good to look at it visually, right? So A to B, B to C would imply that A to C has to exist, and it does. And there's no other link you can make like that, right? Like A to C and C to nothing. Okay, there's nothing else I can make. So unless you can make a link that doesn't work, like for example, if A to C wasn't there, then this would not be transitive, right? Or for example, if C went to D, let's say, if C went to D, then this would also not be transitive, because then you could say A to C, C to D, which would imply that A to D has to be there, but it's not there, right? So this would be not transitive. But based on what was given in the question, this is transitive. And the same over here. Let's take a look. What's transitive over here? So, let's say 2 to 8. Well, 2 to 8 doesn't go anywhere, right? So let's say 2 to 4. Okay, 2 to 4 and 4 to 8 would imply that 2 to 8 has to exist. That's true. That is there, right? Let's see what else, other combinations we can make. 3 to 6 and 6 to 6 would imply 3 to 6, which is fine, right? That is true. And so I think this is transitive. Yep, I think this is transitive. There's no, unless I'm missing a line that I forgot to write. No, I think that's also transitive. Yeah. So you just want to see if you can make, drawing it out is really, really good, even if it's not drawn out for you on the test. It doesn't take very long to draw these things out. So draw it out and see, and with the directed arrows, and see if you can make these links, right? So again, pretty much the only thing I had to check is that if I have 2 to 4 and 4 to 8, then 2 to 8 should exist, right? And it does. If 2 to 8 wasn't there, not transitive, right? 2 to 8 wasn't there. Let's say if we had, 8 to 7. Just say, let's pretend that 8 divides 7, whatever. Then, 4 to 8 and 8 to 7 would imply that 4 to 7 has to be there, but it's not, right? So this would be not transitive. But, again, given what was given in the question, this is transitive. So they're both transitive. Okay. Any questions about this one? It's good to ask these things. So next, what I got for us, it's on my other monitor, is, so because 2 to 3 and 6 to 6, does that imply 3? 2 to 3, but 2 to 3 is not, 2 to 6. So because 2 to 3 and 6 to 6, does that imply 2? Well, we don't have 2 to 3 here. 2 to 6. Okay, so because 2 to 6, and 6 to 6, does that imply 3? Do you mean, does that imply 2 to 6? Yeah, but that's already there. So, okay, so I think what you're saying is, because we have 2 to 6 and 6 to 6, that would imply, so we have 2 to 6. Well, I'll use the actual 2R, or whatever it was. Yeah, it was R. So since we have 2R6 and 6R6, this would imply that we have to have 2R6, which we do. That's the first one, right? We have 2R6. Does that, so not 3, nothing, yeah, okay. Good, sounds good. Okay, so let's move on to, I have some more examples for transitive, because I think this is a point of confusion for some people. So let's try this here. So we just have 3 sets, R, S, and T, and we just want to figure out, and it's a relation on A. So we just want to figure out if this is reflexive, symmetric, transitive, all of them, right? So for part A, let's go through this one. So we have, it's a relation on A, right? So it's 0 to 0, 0 to 1, 0 to 3, 1 to 0, 1 to 1, 2 to 2, 3 to 0, 3 to 3, right? Okay, so, let's draw a graph. Drawing a graph is always a good way to do it. So 0, 1, 2, 3, I skipped a number. 0, 1, 2, 3, oh, no, what am I doing? 0, there's 4 numbers, yes. 0, I don't know what I was thinking. 0, 1, 2, 3. So we have 0 to 0, 0 to 1, 0 to 3, 1 to 0, okay, 1 to 1, 2 to 2, 3 to 0, 3 to 3. Okay, perfect. So let's try to understand, what they say. Is it reflexive, symmetric, transitive? So what do you guys think for reflexive? Is it reflexive? Yep, it is definitely reflexive, right? Because everything relates to itself. Everything relates to itself. So it is definitely reflexive. Okay. Is it symmetric? Yeah. What do you guys think? Yeah, so symmetric would mean that I have an arrow going in both directions for all of them. And, So it is going to be symmetric. This is a symmetric relation here. See, the graph, drawing the graph, it's so easy to see it from the graph, right? That's why I just recommend always drawing the graph. You can find it from here. Like I can see that 0, 0, 1, 1, 2, 2, 3, 3 is here, but I know that means reflexive because, you can kind of imagine that these nodes link to themselves, right? So you'd want to, it's good to imagine as a drawing. And then transitive. What do you think? It's not transitive though. 0, 1R0, 0R3. Yes, that makes sense to me. So 1 is related to 0, 0 is related to 3, but 1 is not related to 3. There's no match like that, right? Yeah, it still can be symmetric even though 2, 3, and 3, 2 did not exist. Yeah, because you just say that if you have any relation, then you have the anti-symmetric. I can't say anti-symmetric, but you have the opposite relation as well. But we don't have 2 to 3, so we don't have to say that 3 to 2 has to be there. We don't even have 2 to 3 to begin with, so you don't need to have either of those. Right? This is symmetric, but it is not transitive, right? Not transitive, because for this reason, you can make some sort of link like this, right? So 1 to 0, 0 to 3, and there's not 1 to 3, so it is not transitive. Okay, let's do part B. Part B is 0, 1, 2, 3. So 0, 1, 2, 3. And 0 to 0. So let me just draw this in now. So it's 0 to 0. 0 to 2, oops, 0 to 2, 0 to 3, and 2 to 3. Yep. 0 to 3, 2 to 3. Yep, there we go. Okay. So again, we are just going to try to figure out if this is reflexive. So reflexive, symmetric, and transitive. So what do you guys think? Give me like a... So not reflexive. It's not reflexive. That's true. It's not reflexive. That's for sure. Okay, what about symmetry? Not symmetric? Yeah. Not symmetric either. Right? And Hanad, you got that for sure, right? The last one, it is transitive, right? It is transitive. Because, make any link, right? 0 to 2, 2 to 3, I have 0 to 3. Is there any other link I can check? 0 to 0, 0 to 2 would imply 0 to 2. Obviously, I have that, right? So yeah, it's definitely transitive. There we go. Okay. So that's that question. Yep, there you go. And then we have a part C. So let's do the part C quickly. So part C is just 0, 1, 2, 3 again. So 0, 1, 2, 3. And the relation is 0 to 1, 2 to 3. So what do you guys think for this one? Symmetric. Yeah, that sounds right. Anyone agree? Yeah. Right? So it is transitive. It is actually transitive. So it's not reflexive. Okay? It's not symmetric, but it is actually transitive. Right? Because I can't, so pretty much it's transitive by default. Like every relation is transitive by default until you can show something that makes it not transitive. So like here, this one was not transitive. We just, by default it's transitive, but then we can show like, okay, if I have 1 to 0 and 0 to 3, then I should have 1 to 3, but I don't have that, so it's not transitive anymore, right? But there's nothing I can show here that makes it not transitive. I have 0 to 1 and nothing from there. I have 2 to 3 and nothing from there either. So it's transitive. It's by default transitive. So there you go. That is everything. So does that make sense why it's transitive here? Again, just by default, it is transitive until you can disprove it, right? So you can show that it's not transitive for some reason, right? For some pair with some link there that's missing. So that's how you would show it. But by default, it's going to be transitive. Okay. Let's do another. Why it's trans? Can I explain why it's transitive? Yeah. Well, I mean, again, because just by default, it's transitive. Right? By default, any relation is transitive until proven otherwise. Right? Until you can show some link. Right? So there's no, like up here, I could show this wasn't transitive by saying, well, I have 0 to 1. I have 1 to 0. I have 0 to 3. So I should have 1 to 3, but I don't have that. Right? So it's not transitive. Did I have another non-transitive example up here? No, these are both transitive. So here, right, there's just nothing to check. I don't have some sort of link like this, right? I don't have any kind of link. I just have 0 to 1. I just have 2 to 3. So since there's nothing to check, it just by default is transitive. It is. You just say yes. Does that make sense? What I'm saying there? Yeah. Okay. So let's try. I have another digraph example, although we've done a bunch already, so I don't know if we need another, but it's okay. Let's just try one more here. Oh, I guess the answer is there. I didn't mean to put the answer. I just meant to put the screenshot of the question. So draw a directed graph for this following relation. The relation is a relation on A, which is 3, 4, 5, 6, 7, 8, and it is x, r, y if 2 divides x minus y. So for example, 2 divides 2, right, obviously, and I can write 2 as 6 minus 4, right? So what that means is that 6 are 2. And because 4, 6 are 4, I meant, sorry, 6 are 4. Right, so I can write those both there. So we're going to just draw a directed graph if 2 divides the difference of the numbers. If 2 divides the difference of the two numbers, then we say they are related, right? If 2 divides the difference. So I have all my numbers here. So 3, how many do I have? I have 6. So 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 8. So like I said, 2 divides the difference of 6 and 4, right? 2 divides the difference. But 2 divides also the difference of 4 and 6, right? Oh, sorry, I think I made it the wrong way. X, R, Y, which means we go from... Yeah, sorry. 2 divides the difference of 6 and 4. That's this one we have right here, right? That's this. But then it's also true that 2 divides the difference of 4 and 6. That's also true. Because 2 divides 4 minus 6, which is a true statement, right? 2 divides negative 2. Again, that is true, right? So that means that we also have an opposite arrow, right? In all directions, right? So let's say the difference of, let's say, what should we do? The difference of, what other one do we have? 5 and 8, 4. Okay, so the difference of 4 and 8 is 4. 2 divides that, right? So 8 minus 4 is 4. 2 divides that. But 4 minus 8 is negative 4, and 2 also divides that. If the difference is even as part of the relation. Yeah, that makes sense. Yeah, that's what dividing by 2 means. Yeah, exactly. So the difference is even then as part of the relation. So it's definitely symmetric. Exactly, it's definitely symmetric. Let's say if there's anything else here. Well, there's definitely more, but let's say if there's anything more that's obvious. So, 6 minus 4 is even. 3 minus 5 is even. So 3 minus 5 is 2. And 5 minus 3 is negative 2. And 2 divides both of those. Right? So I'm just using red to show the negative answer. 7 and 3, that makes 4. Yeah, and 2 divides that. So 7 and 3. Right? The difference is 4. 2 divides that. And negative 4. 7 and 5, that's 2. Yep, that makes sense. So 7 minus 5 is 2, and 5 minus 7 is negative 2. Right? 8 and 6, that's 2 again. Yep, that makes sense to me. So 8 minus 6 is 2. We draw that better. 8 minus 6 is 2. 6 minus 8 is negative 2. Okay. Now anything else? Yes, yes. So there we go. That's an important thing too. 8 minus 8 is 0. 2 divides 0. 3 minus 3 is 0. 2 divides that. 2 divides that. 2 divides that. 2 divides that. And 2 divides that. Right? So that's an important thing too, right? That we have, that it's all, well, it's reflexive, right? It's definitely reflexive because the difference of the same number is 0 because it is not different. And so we just have that 2 divides 0 is true. So there we go. That should be it. Should be it. Looks right to me. This is the cleaner one from the textbook as the answer, but same thing. And now let's just ask ourselves, reflexive, symmetric, and transitive. What do you guys think? Reflexive, symmetric, and transitive. Okay, so looks like okay, good question, Parthraj. I'll get to that in a second. Yeah, symmetric, yeah. Transitive, yeah. Reflexive. So okay, so it is definitely reflexive. It relates to itself. It's definitely symmetric, right? Because everything is a two-way street. And transitive, let's see. Is there any counterexample I can make? Well, if I have 7 to 3 and 3 to 5, do I have 7 to 5? I do, right? And you can kind of see by the symmetry of it that I will always have that transitive there. You can go ahead and check all of them, but you can see by the symmetry that yes, it is going to be transitive here as well. Right? Now, Parthraj asked, how do we prove that it's algebraically reflexive, symmetric, and transitive? It's a great question. I don't think we necessarily need to do that. I don't think he did that at all in the course. We can show, yeah, it's not too bad. Let's go ahead and just do that for a second. Let's just say, side note. I think this one will be fine. Algebraically prove, I know I spelled it wrong, that the relation is, reflexive, symmetric, and transitive, right? So, and he was proving the relation algebraically. Okay, so, oh, for some reason Zoom doesn't like if I right-click something. Interesting. Bonato did not unless I'm remembering wrong, he did not algebraically prove that these things are, reflexive, symmetric, transitive. He just by looking at it, or by drawing graphs like this, you could tell. But yeah, we can do it with this one, not too hard, right? So remember, x, r, y is means that 2 divides x minus y. So first of all, algebraically prove that a r a for all a in a, right? Let's just say that. So a r a, right? A r a would imply 2 divides a minus a, which is 2 divides 0, which is a true statement. So we have proven that it is reflexive, right? So yes, reflexive. Now for symmetric, that means that a r b implies b r a, for all a b in a. So let's start with the hypothesis. So a r b would mean that 2 divides a minus b, right? Which we want to sort of get to this conclusion here, right? So this is logically equivalent to 2 divides negative b minus a, right? 2 divides negative b minus a. Yeah, that's true. And 2 divides yes, and then b minus a minus b. Okay, so we might have to use this by, I think this is fine what I'm saying, but I think we might have to do it differently. Yeah, okay, we have to do it differently. So 2 divides a minus b is logically equivalent to a minus b equals 2k. Is that right? A minus b equals 2k. Yes, a minus b equals 2k. So that just means that, a minus b is some multiple of 2, which means 2 can divide it, right? A minus b is some multiple of 2. So now we need to show that this means that 2 divides b minus a, which is logically equivalent to b minus a equals 2, let's just say k1 and 2k2, right? So this now is logically equivalent, just the whole thing is logically equivalent to negative b minus a equals 2k1, right? And so then I just make multiply both sides by -1, right? Multiply both sides by -1 on here. So this is logically equivalent to b minus a equals 2 times negative k1, right? And so this is still, we started with this, right? We started with, so I guess I didn't need this bottom line. So we started with the hypothesis, which is that, I want to show that this implies that this is true. So we started with this, and I showed that this is logically equivalent, right, to b minus a equals 2k2, which is logically equivalent to b r a. So let me recap that. We started with this statement. Let me box it to sort of highlight what we started with, right? So we started with that. So that is logically equivalent to a minus b equals 2k1, right? Which is just some k, right? But for the first k value. This is true because 2 divides a minus b means that a minus b is, if you move the 2 over here to the denominator, a minus b divided by 2 is some constant, right? So just another way to write that is a minus b equals some multiple of 2. So this is logically equivalent to this just by factoring out a negative sign, right? Moving that negative sign to the other side, right? And then calling negative k1 just some other k2, which it is. It's just some other k2. And this is exactly, we showed this is true, so it's exactly what BRA would mean, right? It's exactly what BRA is there. So again, this is proving, yes, this is symmetric. Yeah. Okay, and then now for transitive. So transitive would be that ARB and BRC implies ARC. And is it transitive? Did we say it was transitive? Yes, we did say it was transitive. So let's show that it is algebraically. So we will start with the fact that we know that ARB is logically equivalent to A minus B equals 2 divides A minus 2K, I meant 2K1. And we know BRC is logically equivalent to B minus C equals 2K2. K1 could be equal to K2. It's fine. Yeah, that's fine. And now we just want to show that we know that that we just want to show that this implies 2 divides A. Well, yeah, 2 shows this implies ARC, which is logically equivalent to A minus C equals 2K3. Yeah. Okay. So if I just add these equations together, right? We know these are both true, so I can add them together to make a third equation. It's going to be A minus B plus B minus C equals 2K1 plus 2K2, right? Then we get that A minus C equals 2K1 plus K2. Just call K1 plus K2 equal to K3. So A minus C equals 2K3, which is exactly what we were trying to get. So yes, it is transitive. So there's algebraically showing that it is reflexive, symmetric, and transitive. Again, Bernardo did not go through an example like this, I don't think, unless I'm remembering wrong. If anyone can remind me if he did. I don't think he went through an example like this. Yeah, he didn't, right? So I would be surprised if it was on the test. Because he said no proofs. Yeah, this is like, yeah, I guess this is a proof, but it's mostly just like showing something by definition. But I mean, it is somewhat of a proof. So one of the practice problems had something like this, though. Yeah, did it really? I have a feeling it's not going to be on the test. Something like showing it algebraically, but I guess possibly. So here's an example, right? You just really just want to do it by definition. You just literally use the definition, right? Reflexive isn't too hard, and then all this other stuff. We can do them for other ones too. Okay. So there is that. That was a good side question there to show it algebraically. So if we draw it out on the test, is it fine? I don't know. I think so. I think so. Yes. If you draw it like this and say yes, reflexive, symmetric, transitive, I think so, because Bernardo did not go through an example like this where you had to show it algebraically. But apparently CPW did. So not sure. Okay. So let's take a look at some more examples that I have here. So let me just mark off on this other page here what we've already done. So we've already done this question, we've done this question, we've done this question. We haven't done these ones. I think if we're given a large set, it might be easier algebraically. Yeah, for sure. Absolutely. Done this, done this. Okay. Let's go ahead and talk a little bit about just quickly what's an equivalence relation, right? Equivalence relation, right? So an equivalence relation is just a relation, which is all three, right? Which is symmetric, reflexive, and transitive, right? And so you can think about them as, a very it's a very close relationship between the two elements there, right? We kind of say that they are almost equivalent to each other, the two objects. So, obviously the equal sign is an equivalence relation, but I think a more interesting one is the parallel. So two lines, L1, L2, being parallel, this is symmetric, reflexive, and transitive. So let's just go through why it's all of those, right? So reflexive, symmetric, and parallel. And this was the most visual understanding for me that I really liked. So we'll go through it here. So it's reflexive because if a line is parallel to itself, right? So if you have a line and you're comparing it to itself, it is parallel to itself, right? That's pretty not too crazy, right? So a line is parallel to itself, right? Okay, symmetric, right? If you have some L1, L2, if line 1 is parallel to line 2, then line 2 is parallel to line 1, right? If line 1 is parallel to L2, line 2 is parallel to L1. That's all it is, right? So if line 1 is parallel to line 2, then line 2 is parallel to line 1. So it is a symmetric relation. And then for parallel, so why did I say parallel? I meant transitive. Transitive. That's definitely what I meant. So if line 1 is parallel to line 2, and line 2 is parallel to line 3, then line 1 is parallel to line 3, right? So again, I think visually it's very like clear. So I'll just draw different colors here. Line 2. So if line 1 is parallel to line 2 and line 2 is parallel to line 3, then of course line 1 is parallel to line 3. They must all have the same slope, right? So I don't know, I'll just use that as my explanation for that one. So this is an equivalence relation, right? Just a special kind of relation that we have. So you can think about an equivalence class, right? All of these lines that we just drew here are part of an equivalence class. Let's say I have the line L, I guess I'll say, L1, L2, but let's say L1 is equal to, L1 is y equals 2x plus 3, right? So the equivalence class of L1 is the set which contains all lines with a slope of 2, right? That's the equivalence class of line 1. Because the equivalence class is just the set of all lines which are related to L1, right? So, if you have any element here and you have some sort of relation, that's an equivalence class, and you just want to have a set which contains all of the elements which are related to L1, right? So more, maybe if you want to see it as like a set notation, you would say this is the set of lines, like say L, M, I don't know, just say L, I guess, L, right? Such that L1 is related to L. Yeah, parallel to L. There we go. It's a set of all lines such that line 1 is parallel to L. So there we go. And then if I had another line 2, which is y equals 2x plus 11, and then line 3, which is y equals 5x minus 2, then we would say that, well, line 1, first of all, line 2 is in this equivalence class. And if I were to make the equivalence class for line 2, right, this would be, well, okay, let me ask you guys. Would this equivalence class be the same or different than this equivalence class, line 1 here? So would the equivalence class of line 1 be the same as the equivalence class of line 2, or would they be different? What do you think? Yeah, they're the same, right? Because again, line 2, L2, has a slope of 2, and so it's parallel to all lines with a slope of 2, right? It's the same definition, right? Exact same definition on both of them. And that comes from the fact that line 2 is in this, right? And line 1 is in this, right? Line 1 is an element of this, right? And line 2 is an element of this. Line 3, right? If I were to make the equivalence class of line 3, right? This would be different now. This would be the set of all lines with a slope of 5. And so you can imagine that we're kind of, by doing this, right? We're kind of like, chopping up. Oh, and so before I say this, line 1 is not an element of this. Line 2 is not an element of this. Line 3 is not an element of this. And not an element of this either, right? Okay, so what we're essentially doing is we are chopping up the set of all lines into infinitely many subsets, right? So one for all the sets, one for all the sets with a slope, sorry, one for all the lines with a slope of 1, then one for all the lines with a slope of negative 2.5, 2.4, whatever, and so on forever, right? Dot 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 for all slopes, right? For all possible slopes. And an important thing, all of these sets, all of these infinitely many, all of these sets are disjoint. I'm sure you understand that, right? All of these sets are disjoint, meaning they don't share any elements, right? So an element in that first set, a set which has all the lines of slope of 1, does not share any elements with the set which contains all the lines with the slope of negative 2.5. There's no shared elements there. And the union of all these sets is the union of all these sets is the original set of all possible lines, right? 2 important points. And so this is the exact definition of a partition. This is a partition, right? So each of these are equivalence classes, right? Each of these are equivalence classes here. They're sets, but remember, equivalence class is a set, right? And they each are a partition of the whole set of all lines, right? Because you have one set for all the slopes of all the lines with slope of 1, negative 2.5, 5, all the other decimals, whatever. They are disjoint. They are all disjoint, these sets, right? Which are equivalence classes. And they are also all, the union of all of them is the set of all possible lines. And that's it. There we go. Okay. So there we have that. That is the example there, which is good. So let's talk a little bit more about equivalence classes. I think there was an example from the textbook, which I just remembered, which I think we might want to do from the actual course textbook. So let's take a look. Any questions while I'm finding this one? Just looking for the problem. There's one problem that I wanted to find. Yeah, okay, here. So which of the following are, I think it's 3.11. I think this is the one. So which of the following relations on 1, 2, 3 are equivalence relations? If the relations are equivalence relations, then describe the equivalence classes. So let's just take a look first of all. For it to be an equivalence relation, it has to be, reflexive, symmetric, and what's it called? Reflexive, symmetric, and transitive. So let's just check, right? Is this reflexive, symmetric, and transitive? We can draw a diagram, obviously, but it's definitely not. Oh, sorry. Yeah. Oh, yeah. Okay, so this is the thing. This is the thing that he mentioned before. He mentioned in the class today, which is a little weird. So what do you guys think? Is this reflexive, first of all? Reflexive. Yeah. Yeah. Right? It is. Well, okay, so it is reflexive. The textbook would say yes. The textbook, like our textbook of this class, yeah. And I think, but he said it'll be more clear on the test, yeah. So it is not reflexive by definition, right? Because if you think about this relation as a relation on X, it does not contain 3, 3. So it's not reflexive. But if you think about this relation as a relation on, A, this other set, which is the set 1, 2, right? Which is a subset of X, right? Then it is reflexive because 3 isn't mentioned here. So we say that actually this relation is not a relation on X. It's actually just a relation on this smaller set 1, 2. But yes, he will phrase the questions better, hopefully, on the test. Because it's a little bit confusing to not know, it says it's a relation on X. So if it's a relation on X, then it would, it should contain 3, 3 to be reflexive. But you have to sort of understand that this is actually implying to you, by the fact that 3 isn't mentioned here, right? That this is actually just a relation on 1, 2 instead of 1, 2, 3. It's actually just a relation on 1, 2. So say relation on relation on. So if it's a relation on X, you have to look at the number of elements inside of the content of each element. So if it's a relation, so if it's a relation on X, capital X, I assume, you have to look at the number of elements inside of the content of each element. Well, if it's a relation on X, you just want to make sure that all of these elements are actually being referenced here somewhere. Like, if it's not, then so 3 is not being referenced here, so you just assume that this is actually just a relation on 1, 2, instead of saying this is actually a relation on 1, 2, 3. If you assume that it's just a relation on 1, 2, then it is reflexive, right? Because there's 1, 1, there's 2, 2. But it's for every element in X. Yeah, right? Yes, I agree that is the definition. So a relation on X is reflexive. Yeah, yeah, I understand exactly what you're saying. Reflexive if, right? Well, it's a relation R on X is reflexive if A, R, A for all A in X, right? Yeah, absolutely. This is true. And so by this definition, right, which is the same definition. So using this definition right here, this is not reflexive. But so to say, this is not true, to say that the relation R is not reflexive on on 1, 2, 3. Let's call this R, obviously. R. Right? 1, 2, 3. It's not reflexive on this. But the relation R is reflexive. Right? I don't know why OneNote does this all the time now. Come on. Sorry, I don't know why it's doing this. Okay. The relation R is reflexive on 1, 2. Right? And so since 3 is not mentioned here, we just assume that it's actually the second case here. And again, hopefully on the actual test, it'll be phrased better. So it's not so, you don't have to make such an assumption. Right? Like, you don't have to make an assumption that literally contradicts what the question's saying. But at the moment, you do have to do that for this question. Right? Okay. So this is reflexive. This next one's also reflexive, actually. Right? This one's also reflexive. The same reason. Exact same reason. Now, these ones are also, they're all reflexive. So these are all reflexive here, right? Because the last two actually have 1, 1, 2, 2, and 3, 3, right? But the first two don't have 3, 3, but it's okay because 3 is not mentioned anywhere. So they're all reflexive. Let me move this to the side here. Okay, so we've established that they're all reflexive. I don't want to make it too messy, so I'm just going to copy all of them again. Now, symmetric. Okay, so that means if you have 1, 1, you have 1. Well, okay, that's not a good example. That means if you have 1, 2, you have 2, 1. So this one is not symmetric, right? This one is symmetric. This one is not symmetric, right? And this one is symmetric. Does that make sense? My choice here for symmetric, not symmetric, symmetric. So this one is symmetric, this one is symmetric. Good. So the reason here, this is not symmetric because it has 2, 3, but it doesn't have 3, 2. What I just said there. There you go. So because it has 2, 3, but it doesn't have 3, 2. Right? It's just not symmetric. First one's not symmetric because it doesn't have 2, 1. Right? And that's it. Okay. So far, the B and D are candidates to be equivalence relations, right? So we just have to see if they're transitive, right? So transitive, right? Transitive. But B was reflexive. Yeah, B is reflexive, right? Because it has 1, 1, 2, 2, and we don't care about 3, 3 because 3 is not mentioned anywhere here. For the same reason that this is reflexive. Make sense? Okay. So, from here, yeah. Well, it's the same definition. It's just that we have to make an assumption. We're making an additional assumption. It's not stated in the question that if the relation doesn't mention one of the elements from the set, we just consider that it's a relation only on a subset of it, the subset 1, 2. So for both of these, it's not actually a relation on X. It's a relation on 1, 2, which is a subset of X. Right? So again, it's the same definition, but you're just changing what the actual set is that you're working on, the relation's working on. Okay, and then finally here, transitive. So I'll draw a graph for this one. I mean, it's good to draw. For transitive, it's gets really messy, right? Obviously, so 1 and 2, right? So we have 1 to 1. Let's just draw. This is 1. This is 2. So 1 to 1, 2 to 2, and 1 to 2. So the only link we can make is 1. Well, actually, I guess I don't have to even check this one because we already know it's not going to be an equivalence relation, but it's not transitive. Well, let's see. So it's 1 to 2, and 2 to 2 would imply 1 to 2. That's it. So it is actually transitive, right? It is transitive. But it's not an equivalence relation because it's not symmetric, so we don't even have to check that. The question was asking which ones are equivalence relations. But let's check all of them, whatever. It's good to just get practice. So then this one is, again, just between 1 and 2, right? So we have 1, 2. So we have 1 to 1, 2 to 2, 1 to 2, and 2 to 1. So this one is definitely transitive as well. Oh, is it transitive? Yes, it is transitive as well, right? Because what are the links we can make? 1 to 2, 2 to 2 implies 1 to 2. Okay, that's there, obviously. So now 2 to 1 and 1 to 1 is there. So is 2 to 1 there? Yeah, of course, that's what we started with. So it's also transitive. So it looks like this B is an equivalence relation because it is symmetric, reflexive, and transitive. Now let's check this part C, right? So this is now 1, 2, and 3. Okay, 1, 2, and 3. So I always forget to actually put the numbers on. So we have 1 to 1. We have 2 to 2. We have 3 to 3. We have 1 to 2. We have 2 to 1. We have 2 to 3. So transitive, what do you guys think? Is this one transitive? No, it's not transitive. Yep, that's right. So we have 1 to 2, we have 2 to 3, we do not have 1 to 3, so it is not transitive. Okay, not transitive. Great, and then this last one here, right, which is just the same thing. So I have 1, 2, 3, right? So 1 to 1, 2 to 2, 3 to 3, 1 to 2, 2 to 1, 1 to 3, 3 to 1, 2 to 3, 3 to 2. There we go. Is this one transitive? Yep, it's transitive. Yep, exactly. Right. So B and D are both equivalence relations. Okay, so B and D are both equivalence relations. I don't get transitive for A. For it to be transitive, shouldn't it also work the other way? Yes, which one? Let's see. So, well, okay, so you're saying because 2 is related to 2, so 2 is related to 2, but 2 is not related to 1. That's an important thing, right? So for B, it goes the other way, right? Which just means that we have 2 links we can check. We have 2 links. We have the first link, 1 to 2, 2 to 2 implies 1 to 2, and separately, 2 to 1 and 1 to 1 implies 2 to 1, which we have for both of those. But here we only have one link that we can create. 1 to 2 and 2 to 2 implies 1 to 2. Which we have, so it is transitive. There's nothing else to check. So if it's not transitive, right, then you have to be able to show some kind of 1 to 2, 2 to 3, and you don't have 1 to 3, right? Something like that. Right? But here they are transitive. Okay. So yeah. Okay, so A and D are both equivalence relations. Great. And so now it says describe the equivalence classes. Describe the equivalence classes, right? So we have, yeah, so, okay, so for B, we have the equivalence class of 1, let's say that, right? So the equivalence class of 1 is all the elements which are related to 1. Let's look at B, where's B? B's here. So all the elements which are related to 1. So 2 is related to 1, and 1 is related to 1, right? So 2 and 1, that's it. And the equivalence classes of 2, right? What's related to 2? Well, 1 is related to 2, and 2 is related to 2. So 1 and 2 as well, right? And that's it. But of course they'd be the same because 2 is in the equivalence class of 1, which means that the equivalence class of 2 is going to be the exact same thing, right? Because remember, if an element like this is in the equivalence class, if this line is parallel to this line, right? Then of course, if you ask what are all the lines parallel to this one, it'll be the same thing, right? It'll be the same thing. If you think about them like lines. I like thinking about them like lines, right? So if we're asking, what are all the lines parallel to this one? Well, it's itself and this other line. So what are all the lines parallel to this other line? It's the same set, right? Same set. That's all it is. And then for D, we have the equivalence class of 1, which is just going to be, so this is D over here. Yes. So for here, we have what's related to 1. Well, 1 is related to 1, obviously. 2 is related to 1, and 3 is related to 1. And since all of them are there, right, then this is, of course, the same as the equivalence class of 2, and it's the same as the equivalence class of 3. And that's all it is. Yep, that's correct, what you said. And there's that example down there. Okay, maybe drink some water, and then we will continue. Let's actually do this 3.12. Is there any particular homework questions you guys want me to do? We'll just talk a little bit about functions, I guess, soon. But for now, we'll keep talking about this. This is a good one, too. Let X be the set A, B, C, D, E, F, G, and let the set, which is the set A, C, E, the set B, and the set D, F, G, be a partition P of X. So first of all, it is a partition because those are mutually disjoint sets whose union is X. Right? Mutually disjoint sets whose union is X. Determine the equivalence relation induced by RP. So RP is just the equivalence relation, right, which causes this partition, right? Which causes the equivalence classes here, right? So first of all, the equivalence class of A, which is equal to the equivalence class of C, which is equal to the equivalence class of E, is equal to the set A, C, E, right? And then the equivalence class of B is just equal to the set B, right? Oops, the set B, right? And then the equivalence class of D, which is the equivalence class of F, which is the equivalence class of G, right? Which is equal to the equivalence class of G, is equal to D, F, G, like that, right? So again, think about it in terms of lines, right? If A, C, and E are all parallel lines, right? That means that if we ask, what are all the lines parallel to it in this set, right? Not all possible sets, but just these sets, right? Let's say A, C, and E are all, the fact that they're in a partition like this, the fact that they're in a set means that they share, they're all parallel, right? Then, what are all the lines parallel to A? That's A, C, and E. What are all the lines parallel to C? Also A, C, and E. What are all the lines parallel to E? Also A, C, and E. Right? But not parallel to B. B is in a different partition there. So the equivalence relation is just to say that, remember, if the equivalence class of A is A, C, and E, what that means is that in our relation, RP, right, we're going to have A, we're going to have A, C, we're going to have A, E. Okay, that's from this. And then we're also going to have, the opposite too. We're going to have C, C. We're going to have CA, and we're going to have CE. Okay, we're also going to have EE. We're also going to have EA, and we're also going to have EC. Okay, that's everything. This first chunk here is what you get from these guys, right? Which is just saying A is parallel to, I like thinking about them like lines. So A is parallel to A, of course. A is parallel to C, yes, because they're in the part of the same equivalence relation. A is parallel to E, C is parallel to C, and so on. Then from this block here, we just get that B is in this ordered pair is there. And then from this last one, we also get a whole bunch. We get the same from the first time. So we get D is related to D, right? D is related to F. D is related to G. We get F is related to F. F is related to D. F is related to G. We get G is related to, did I miss something? No. We get G is related to G. We get G is related to D. And we get G is related to F. And that's it. And that's the answer. That is the equivalence relation, RP, which makes this partition. So kind of a confusing question because it's kind of hard to think about it. but basically what you do is you just make all the pairs you can, right? The fact that these are in a partition means they're all related to each other. A is related to A, right? A is related to A is related to C, A is related to E, then C is related to C, C is related to A, C is related to E, and then so on. And you do it for all of them. Here it's just B is related to B, that's it, and then you do it all for that. So you just kind of make all the combinations you can, right? Or all the permutations you can. And yeah. So there we have that. Okay, so that's that question done. If there's any questions, let me know. Otherwise, I will continue on with some other questions I have here. So I showed the parallel relation. Oh, I didn't do any partial orders yet. Let's do partial orders. I did this. Can skip that. Okay, let's do partial orders. Let's move on to partial orders here. So to make sure, a set with one element is always going to be equivalence relation, right? Let's say you have an X, which is 1, 2, 3, and you have R, which is 1, 2, right? Like this is what you mean. So this is non-equivalence relation, right? Because one is not related to itself, 2 is not related to itself, right? 1 to 2 does not imply 2 to 1. We don't have 2 to 1. Okay, let's say now if you had 1, 1, now this is reflexive, it is symmetric, and it is transitive. So this is an equivalence relation. Yep. But this is not an equivalence relation because it's not symmetric, it's not reflexive, and it is transitive, but it's not the other two. Does that answer your question? Yeah, okay. So this, if it's like 1, 1, 2, 2, 3, 3, something like that, yeah, then that is an equivalence relation. Okay, let's move on to partial orders. So partial orders. What's going on? There we go. We have, again, from this textbook. So testing for anti-symmetry of finite relations. First of all, anti-symmetry is an important part. So partial order is just like another kind of relation that is reflexive, anti-symmetric, and transitive. So let's just check if these are anti-symmetric, right? So I'll do it by drawing a graph of the relation, right? So these are relations on 0, 1, 2, right? 0, 1, 0, 1, 2. So 0, 1, 2. So for part A, we just want to determine, is it anti-symmetric? So let's just draw it to get understanding. So 0 to 2, 1 to 2, oops, 1 to 2, okay, and 2 to 0. So now, what is anti-symmetric? Anti-symmetric, oops, didn't mean to open that. I have my notes here. So anti-symmetric is, let me get the actual order here. Let's get the actual definition that I have from my notes. Okay, so essentially the idea is, let R be a binary relation on A. We say that R is anti-symmetric if A R B and B R A implies that X equals Y. Oh, X equals Y. Should be A equals B. That is incorrect. It should be A equals B here. So I'll fix that after. So yeah, implies that A equals B. So the only way that you have any kind of symmetry is if it's the same element. But if you have symmetry otherwise, if for example you have 1 is related to 2 and 2 is related to 1, it's not anti-symmetric, right? So this, what do you guys think? Symmetric or not? Sorry, anti-symmetric or not anti-symmetric? So is it anti-symmetric? It is not anti-symmetric, right? Yes, there you go. So anti-symmetric, right, is a big no, right? Symmetric. It's a big no, right? Not anti-symmetric. Because you have symmetry, which is not between the same element, right? You have, so in anti-symmetry, if you have anti-symmetry, the only time you have symmetry is like 1, 1, 0, 0, 2, 2. That's the only time you have any kind of symmetry. Otherwise, you can have no other symmetry. So here we have symmetry, 0 to 2 and 2 to 0. That is a symmetrical part of the relation, and so it is not anti-symmetric. B is, again, a relation from 0, so 0, 1, 2. We have 0 to 0, 0 to 1, okay. 0 to 2, 1 to 1, 1 to 2. So what do you guys think? Is this anti-symmetric? Yep. So you got one yes. Yeah. The guys too, Ethan too. Yep. Yep. And then, yep. Looks like good. Yep. This is anti-symmetric, right? Anti-symmetric. Because the only time we have symmetry is between one of the nodes and itself. I don't have 0 to 2 and 2 to 0. I don't have any kind of two-way path here, right? If ever I have a two-way path, right, that's not just to itself, because obviously everything is symmetric to itself. Other than that, we don't have that in this graph. So it is anti-symmetric. So anti-symmetric doesn't just mean not symmetric. It means that there is not even a part of it which is symmetric. So it's really like the absolute opposite of symmetric, right? Again, not just not symmetric. That's not the same thing. Saying not symmetric and anti-symmetric are not the same ideas. Not symmetric just means that somewhere you have a non-symmetrical relation. So, like, I mean, this is not symmetric either, right? It's also not symmetric, right? So because you don't have any kind of symmetry in for all of these here, right? But in like an example, like if I take this, right, this is anti-symmetric, and let's say if I added this here, right, then it would be symmetric. Would it be symmetric? Yeah, it'd be, well, okay, I'll just be, oh no, never mind, doesn't have to have that. There you go. So yes, so this now would be symmetric, but still anti-symmetric, right? Okay, so there we go. That is just making sure we're able to identify that things are anti-symmetric. So now if you have a relation which is anti-symmetric, reflexive, and transitive, you have a partial order. Can I do the algebraic proof for anti-symmetric? Okay, let's try this. So we know this one's anti-symmetric, so that means, well, the thing is I don't have a definition. This is actually all I could do for this one, I think, is just by exhaustion. Just go through it and just see, is there any two-way street, right? So there's nothing I can do for this one. If I had a relation defined, I guess I have it in the next part here. So let's try with the next one. Don't know if I'll be able to do it. It might be a little bit too complicated to do algebraically, but I'll give it a try for sure. So for this one I can't, because I just have to do it by exhaustion here, just like exhausting all the points. So consider the subset relation, on the set power set of ABC, that is for all sets U and V in U is a subset of V, is for all X, if X is in U, then X is in V, right? So it's just a subset. It's just a subset notation, which is a partial order, right? Because, for example, it's anti-symmetric, definitely, right? Because if, we have that A is a subset of AB, right? A is a subset of AB, but AB is not a subset of A. Never. It's never the opposite, right? So it is definitely anti-symmetric. Sorry, it says not never. It is only that if it's itself, right? So I should be clear here. It is also the opposite if it's itself, and that's fine. Remember, we said that's fine, right? We said that's fine if it's the relations to itself, right? The symmetry is to itself, but it's never symmetrical to a different set, right? Okay, so we want to draw the Hasse diagram for this, right? Which is just a way to represent this. So to draw the Hasse diagram, what you want to do is you want to, okay, you can jump right to the Hasse diagram, but let's look at it like, let's first draw it as a graph, and then see how we can turn that graph into a Hasse diagram. So the power set of A, B, C is equal to the set which contains the null set, the set which contains A. Did I already write this somewhere? I think I wrote this exact thing. The power set of A, B, C. Yes, I did. There we go. Let's just use this. Oh, OneNote's freezing on me. That box is not supposed to be there. Okay, I will restart here. Sorry, that was probably an alarming effect of the thing. There we go. No, that's not what I want. There we go. Okay, let's try that again. There we go. So, scroll all the way back down. I mean, it's a little ugly how I wrote it, but obviously I could draw that a little bit better. Now I feel like drawing it better, but okay, whatever. Let's just leave it. I'll just move this up here at least. Oops. There we go. So there we go. Draw the Hasse diagram. So what we want to do is all of the elements, we have a relation on this set, right? So we're going to have the null set, right? We're going to have the null set. We are going to have the set A, B, C, right? So the set A, the set B, the set C, right? I guess I should draw them next to it. Set B, the set C, right? And the set A. Then we're going to have the set we're going to have the set AB. We're going to have the set I wrote AC twice. Whoops. I meant BC. Okay, BC. And I will have the set AC here. Okay, the set AC. And then finally, I'm going to have the set ABC there. Okay. So now we draw all of the relations here, right? We draw all of the relations. So again, this is not the Hasse diagram yet. I'm just going to draw the graph, and then we're going to turn that into a Hasse diagram. So first of all, something is a subset of itself always, right? Something is a subset of itself always. Subset is a subset of the null set is a subset of the null set, right? They're all subsets of themselves. So there we go. There we go. Okay. Next, the null set is a subset of every set, right? So I will draw this like this, and then I'll just have to go around like that. There we go. Okay, then we have that. You know what? I should draw this a little, not differently, but how about I color code it just a little bit? I'll just do the reflexive stuff is just in green. There we go. Just want to be a little bit legible. There we go. Okay, and then from the null set, that's like the first level of inclusion there. Then we have that A is a subset of AB, right? A is also a subset of AC. B is a subset of AB. B is a subset of BC. C is a subset of BC. C is a subset of AC. So you see it's getting messy very quickly, right? So there's a reason we do Hasse diagrams instead of this. These are all subsets, right? So these are also all subsets of this, right? And am I missing anything? No, that's everything. There we go. So there's the whole graph of it, right? Obviously, I can do this a little bit prettier. Here's the graph from the textbook. But all you do is you just match, draw a line. If, from, AC is repeated twice in your B set, you missed. Oh, yeah. Sorry. That was probably from 2 minutes ago. Yes, it was 2 minutes ago. There you go. Just saw that now. So there you go. There is your graph of this, pretty much what I drew, a little bit nicer. But the way you turn this into a Hasse diagram, okay, first of all, actually, I even did something here without even mentioning it. I draw all the arrows pointing up. That's important, right? Draw all the, okay, inclusion to itself, it doesn't matter. But all the arrows of inclusion like that, you want them all pointing up if you're going to turn this into a Hasse diagram. So then what you do is you take your drawing, right? You take your drawing and you just say, okay, the reflexive implied. Let's just say that's implied, okay? The reflexive is implied, that everything's reflexive to itself. And transitive, any transitive line is also not important, right? So if null set to B, null set to BC, null set to ABC, I don't need this line, right? Because transitively it is true, right? I can use just a transitive property here that, if null set is related to B, B is related to BC, then null set must be related to BC. Oh, I even forgot to draw that originally, right? So yeah, the null set. Oh no, I didn't forget to draw that. Right there. There's the line. So I don't need that line either, right? I don't need this line. I don't need this line. Because I didn't need this line because A null set to A to AB, that already implies this line, right? Because we know it is a well, I guess I didn't say it's here. It is reflexive, anti-symmetric, and transitive. Let's just put that here. Let's just say this is a partial order. That's the word I'm trying to say. This is a partial order, right? Okay. So now I can, again, keep removing things. So I don't need this because that's a transitive line. I don't need this, this, and this transitive line, right? I think I need to leave, let's see, what do I need to leave? So B to this, I think I need to leave that. Let's see, anything I'm missing? A to AC is fine. Everything else I think might be needed here. See, anything else that's not needed here? Yeah, I think that's everything. If there was a symmetric relation, we remove that as well. Well, you wouldn't draw a Hasse diagram if there was a symmetric relation, because then you can't draw all the arrows pointing up, right? That's an important thing. So the Hasse diagram like this is only for partial orders, which are anti-symmetric, always anti-symmetric. So not at all symmetric. Okay. So now we have this. I think that's the final thing, unless I'm messing up something, but I don't think I'm messing up anything. So this is the diagram like this, right? This is the diagram from the textbook, which is, basically what I drew. So here we have, the null set at the bottom, then A, B, and C. So the null set goes to A, to B, to C. Then from C, we go to BC, which is there, which is what I have. And from C, we go to AC, right? C, we go to AC. That's true, right? From B, we go to AB and then BC. So from B, we go to AB and then BC, right? And then from A, we go to AC and AB. So we go to AC and AB. Then from AB, we go to ABC and B. Well, that's fine. I don't have to go down. Let's just check what's going up, right? So we go up. From AC, we go up. From BC, we go up there. So it's all right. Yes. We do remove all the directional arrows because it's implied that the relation is you're going upwards here, right? There's sort of like the height kind of matters in this case, right? So you remove all the arrows here, right? The arrows don't matter. You still draw a line, but you just don't draw arrows because you just implied that everything's drawing upwards. It doesn't matter. There we go. And there's our Hasse diagram. Yes, that is fine. Okay, mine's a little twisted compared to theirs, but it's fine. Same thing. So we can now ask certain things like, is there a greatest element, right? Some greatest element is an element which is greater than all other elements in the set. So let me draw that. Let me get the actual definition for all these things, right? You can ask about, so a greatest element. Is there a greatest element here? What do you guys think? Is there a greatest element for this? Yeah, ABC, right? ABC is the greatest element because it's an element A, which is an A. It is the greatest element if for every B, B is less than A, right? So you say that, okay, AB is less than A. So the less than is not like a literal number less than. It's just like you're comparing it. It's literally drawn below it, right? Literally drawn below it, right? A level down. How many levels down are you? So it's a level down from AB. So this is greater than AB. ABC is greater than AB. But maybe a level down or a level up probably is a better way of saying it. But that's not how we say it. So we use this little symbol like this to represent, well, okay, I can't really draw it. There you go, a little symbol like that to just represent that we're comparing things, right? So one is literally like above the other, right? We just draw it visually like this, right? So we have that, we have that, we have that, we have that. But remember, transitive lines are implied. So it's implied that the set C is in fact, you compare it to the set A, B, C. Even though I don't have a line like this, it's implied, right? And so we say they're still comparable, like that. So the greatest element is definitely this. This is the greatest element. And this is, well, what's the least element? The least element is something that is smaller than everything else, right? The empty set is the least element, right? And do we have a minimal element? Do we have a minimal element? A minimal element is either, pretty much a minimal element is just an element that has nothing else below it. Yeah, so it's also minimal, right? Minimal. And ABC is also our maximal, just nothing above it, right? That's all it is. Maximal, there we go. Okay, that's that example. Of course, any questions, feel free to let me know. Otherwise, I will move on. So here, right? We have a partial order relation R has the following diagram. So Hasse diagram. Find the directed graph, and then I'm going to add this. I'm going to add on, let's actually define the relation. Let's say we had one element which did not share a transitive relation. Would that be disconnected from the hierarchy? If you have one element that does not share a transitive relation, then the whole thing is not a partial order, and you don't draw a Hasse diagram. It has to be transitive. Everything. If you have any point where it's not transitive, then the whole thing's not transitive anymore, and you wouldn't draw it as a partial order. We should not share a transitive relation. Would that be disconnected from the share? Does that make sense? Yeah. Okay. So now we just want to figure out the directed graph. So the directed graph is going to, first of all, share all the lines, right? It's going to share all these lines like this, all pointed upwards, importantly, right? Then we're also going to be related to ourselves. Everything is related to itself. Everything is related to itself, right? And transitive lines, right? Transitive lines means that if A is related to D and D is related to F, then A is related to F, right? If A is related to D, and, well, this isn't backwards here. So if B is related to D and D is related to F, then B is related to F. B is related to E, E is related to F, B is related to F, or, yeah, I already said that. I don't have to say that twice. If C is related to E and E is related to F, then C is related to F. B to F to G means B to G. A to D to F to G means A to G. A to E to F to G means C to G. B to E to F to G means that. And there we go. I think that is our, I think that is everything. I don't have the answer for some reason. I didn't put it there, so. I think there's nothing I'm missing. Oh, okay, sorry. And then I have D to G as well, because D to F to G. E to F to G means E to G. And that's everything now. So obviously, if it's a partial order, you have a much cleaner diagram as a Hasse diagram, because there's a lot of things just implied. You don't have to write all this. So the orange here is my transitive lines. The red the red is my just normal, relation lines, and also the reflexive lines. Notice there's no arrows down, right? Okay, the reflexive arrows kind of point down, but there's no actual arrow down. Okay, and then to figure out the relation R, which defines this, right? The relation R, well, it's just a bunch of ordered pairs, right? So, A is related to A, then we have B is related to B, right? And so on for all of them. I'll just say and so on, right? All the way to G is related to G. Then we have A is related to D. D is not related to A though, right? D is related to F. Then F's related to G. Oops, F's related to G. Then we have C is related to E. We have E is related to F. And I don't have to say F related to G again. I already have that. B is related to E. B is related to D. I think that's everything. And then we just had to have all the transitive ones, right? So I'll just say plus all transitive ones. Dot, dot, dot. Right, dot, 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 all transitive. And then close set, whatever. Right? All the transitive lines. I'm not going to draw all of them, but yeah. So that would be the relation R there. Okay, that is that. I have one more partial order. So I'm going a little fast just because I want to cover a bunch of content, but if anyone wants me to explain anything again, feel free to let me know. Maximal, minimal, greatest, and least elements. So we have a set A, B, C, D, E, F, G, H, I. We have partial orderings with the partial order thing there, defined by the following Hasse diagram. Find all maximal, minimal, and greatest elements. Okay, so let's start with the maximal elements. What do you think is maximal? G is maximal. Anything else? Nothing else. Yep, good. Yeah, that's exactly right. Minimal. C, D, and I is right. Yeah, C, D, and I. So I'll explain why, right? So G is maximal because there's nothing comparable above G, right? Nothing comparable above G. And and C, D, and I are minimal because there's nothing comparable below C, D, or I. So you might say that, well, if you really are thinking about this in a visual way, you might say to yourself, well, I is literally drawn above C and D. But what you want to think about is, is there anything comparable below it? Comparable below it. That's an important thing. Not just literally below it, but comparable below it. So I is not comparable to C and D, right? There's no remember, all the arrows point upwards. There's no chain to get to I from C and D, right? There's no chain to get to I from C or D. So again, because all the arrows have to point upwards. So I is not comparable to C and D, and so I is still minimal because there's nothing comparable, right? There's nothing comparable, like that's comparing to it there. Then we have greatest. What is our greatest element? Do we have a greatest element? What do you guys think? G, yep, not very good. That's right, yeah. And then our least. Do we have a least element? Yeah, we have no least element. There is no single element that is less than all the other elements. If I, for example, combined all of these, right, and made J here, now we have a least element, J, right? J is less than everything else, but we don't have J, so it's not there. If the question asks for the minimal elements compared to E, would it just be D? Okay, that's a good question. Yeah, minimal elements comparable to E would just be D. Just be D? Yes, would just be D. Yep. So the minimal elements that are comparable to E would just be D. So you just look at your same list of minimal elements and just ask which ones are comparable to E. C? No. C is not comparable because I can't draw a line that gets to E from C, right? I can't go down, right? Can't go down. So you can only go up. And so D, but D is comparable and I is also not comparable because you can only go up, right? What's the difference between greatest, maximal, and same with minimal and least? So maximal just means you have nothing above, right? There's nothing above. So if I had, for example, right? Well, yeah, there's nothing above. So G is maximal for sure. There's nothing that is above G. But G is also the greatest, right? Because everything else is less than G, right? So this means there's nothing above G. This means everything else is less than G, which is true. Everything else is less than G. If, for example, I had, J here, then I would have no greatest, right? Because there is not a single element that is greater than every other element. But my maximal would be G and I. G and J, I mean. G and J. Right? But I'd have no greatest in this case. Right? If there was a J there. But I do have a J there. I mean, sorry, but I don't have a J there. So it's just a G. And then similarly, minimal just means I have nothing below it. There's nothing comparable below it. Least means that it is less than everything else, right? Again, this, if I made a J here, that would be the least element now. But now I just have three minimals. And so to be clear, if this was a J here, this would be the least, and my only minimal would be J. C, D, and I would not be minimals anymore. But I do have C, D, and I, right? And I have no least element here because there's not a single element that is less than all the other elements. Okay, sounds good. Okay, I have CPW's practice work too, which might be good to do, but question 1 we already went through. We don't have to do that. Let's see this. Maybe the function question might be good. If you have a greatest, would that mean that the value is the only maximal? Yeah, that makes sense to me. If you have a greatest element, would that mean that that value is the only maximal? Yeah, because if you had, this is our greatest, right? It's also the only maximal. If I had another maximal, let's say like right here, right? Let's say I had another maximal here, which is J. That would also be maximal because nothing's above it, right? Nothing comparable above it. But now I don't have a greatest element, right? I don't have a greatest element. So I'd have two maximals, but I would have no greatest. But that's not what we have. Yeah, that makes sense what you're saying. Okay, let's look at the last one. Okay, I mean, like this takes 2 minutes, so let's just go through it quickly. Obviously I know some people have CPW, so I'm not gonna spend too much time on this, but for people who have banana, we didn't go through this. Consider the following graph, find the order and size of the graph. So we just gotta find the definition of order and size. So if I just go back up to my notes here, right? So, oops, I went too far. So, where are we? Did I write it down somewhere? Did I not write it down somewhere? There we go. So a graph is composed of an edge set and a vertex set. The order of a graph, the order of the whole graph, not the order of a node, but the order of the whole graph is the magnitude of the vertex set. So the order of this whole graph is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So the order is just going to be 10. It's just the number of vertices. And the number of edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right, is going to be the size. And that's it. Just the number of edges. So you do count, if you have multiple edges, you do count them as multiple edges. In this graph, how many vertices have a degree of 2, 3, 4, 5, and 5 respectively? So which vertices have a degree of 2? Degree of 2. So let's see. Degree of 2 means you have 2 edges coming from that vertex. So vertex 1 has a degree of 2. Vertex 2 has a degree of 2. Vertex 3 has a degree of 3. So let's just actually do it like this. We'll just say degree of 3, degree of 4, just put here, degree of 5. Okay, and I'll just do it like, you know what, I'll just here. So degree of 2 is V1, V2, and anything else? Okay, well, let's move V3. V3 has a degree of 3, right? V3 for sure. V4 has a degree of 3. V5 has a degree of 4, right? Because, yeah, 1, 2, 3, 4, right? So V5 has a degree of 4. There's 4 edges coming from it. V6 has a degree of 3, right? V6. V7 has a degree of 2. V8 has a degree of 1, 2, 3, 4, right? So V8. V9 has a degree of 1, 2, 3. 3? V9? Is that 4? Let me check what the answer is. V9 is 4. Okay, so you count as 2. So I just thought I forgot for a second if you count as 2 or not. Yep. So you have 1, 2, 3, 4 edges coming from it, right? So it's going to be V9 there. Yeah. So a loop counts as 2 edges that are coming from the node. And then degree of V10 is a degree of 1. So they didn't ask for a degree of 1. So we have that. There we go. So there's none with a degree of 5. And that's all. Yeah. Okay. Good. So I just wanted to make sure that we go through that so people remember this, but that's everything. That's the whole thing. And remember, just a simple graph, the definition of a simple graph. So size is 14. Oh yeah, the size should be 50. Well, okay, so the size is going to be, so the sum of the degrees of all the nodes is 2 times the magnitude of the edge set, right? Which is 2 times the size, right? So the sum of the degrees would be, so we get 2 plus 2 plus 2 plus 3 plus 3 plus 3 plus 5, sorry, plus 4 plus 4 plus 4 plus 1, right? Plus 1, which I didn't include there, right? And then add that together. Okay, I guess I won't use my calculator. So 5, 10, 15, 20, 28. So this is 28, right? Yeah, thank you. Yeah. And then that is equal to 2 times the size, right? So the size is going to be 14. I'm just using the theorem that we learned, this one. The only theorem we have for graphs is this. Yeah, exactly. Yeah. Okay, yeah, good. That makes sense. Good. I'm happy. So that's that there. We got a couple more minutes left. I think let's just do, there was the last question in functions I liked. I really like that question. So let's do this. Let's describe, let's do this for the last couple minutes here. Describe a bijection f n to z. Well, that's it. That's all we need. That's the only requirement, is that we have a bijection which goes from the natural numbers to z, to the integers. So remember, a bijection means it's 1-to-1 and onto. So 1-to-1, 1. What that means is that every element of Z has only one element of n which maps to it, right? That's what that means. And then it has to also be onto, which just means that every element of Z gets mapped onto, right? Gets mapped onto by the function f, obviously. So the way you want to think about this is just look at, okay, I'm taking the set n, right? N being 0, 1, 1, 2, 3, 4, 5, 6, 7, dot, dot, dot. And I'm mapping this to -4, -3, dot, 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 -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, dot, dot, dot. So we want some sort of bijection. Okay, so wouldn't such a relation be impossible because the relative size of Z is greater than the relative size of N? So definitely that's a thought. That's definitely like something that makes sense. Like intuitively, you'd say that this set is big. This set is bigger than this set. But by the fact that we are going to make a bijection, it actually proves that they have the same size. I mean, they're both infinite, and it's the same kind of infinity. So they actually have the same size. Okay. They have the same, yeah, the two sets have the same size. And we're going to prove that by the fact that we can make a bijection. If you can make a bijection between two sets, that means they have the same size. So let me show you how the bijection would work. I mean, if you have a bijection, okay, I have a kind of a feeling I had is that 0 would have to map to 0. This is how I kind of dealt with it. 0 would have to map to 0, right? And then I was thinking that, okay, so it gives a hint. Consider how to define f on odd and even non-negative integers, right? So that means that, okay, so you see how here I took 0 and mapped it to 0, right? So one possibility is, remember, these are all even. I'll just highlight in pink the even ones, right? Even ones, and then yellow will be the odd ones, right? So here, I mapped even to itself. So maybe I want to map all the evens to themselves, right? Maybe that's what I want. I'm not saying that's what's going to be as the final answer, right? Maybe I want to map all the even numbers to themselves. Okay, but then what do I do? Because then I could map, maybe I could map the odds, you know, maybe here's an idea. I could map the odds to the negatives of themselves, right? Maybe the negatives of themselves here. So maybe you go like that. But I'm missing a whole bunch, right? I'm missing all the even negative numbers, and I'm missing all the odd positive numbers now. So this won't work. So another thing you could do, right, is to say that maybe I'm going to map, okay, I'm going to map the even numbers. The even numbers will be counting, let me make sure I'm going to say the right thing here. Yes, the even numbers of this set. Remember, this set up here is n. This set is here is n. This set here is z, right? So the even elements of n will be counting the positive z's. So let me explain what I'm saying here. 0 will go to the 0th number in z, the positive z. 2, which is the second even number in n, will go to the first number, positive number in z. So we're going to go here. 4 will go to 2, 6 will go to 3, 8 would go to 4. And so using this, we've essentially mapped all the even numbers, right? Map all the even numbers to the positive integers. Okay? I still have half of the natural numbers to work with to deal with all the negative ones. But what I've done is all of the positive integers are being mapped onto now, right? How exactly? Well, I take, so if I say f of x, so if x is, well, I'll say f of n. If n is even, then I want to output n over 2, right? 0 to 0, 2 to 1, 4 to 2, 6 to 3. You're just dividing by 2. 8 to 4. But notice, I haven't done anything if n is odd. I haven't done anything there yet, right? All my odd numbers are still, you know, I haven't done anything with them, right? And they're all ready to map onto our negative numbers. So what I would do now is, first of all, I want to make it negative. So I'm definitely going to have some kind of negative n, right? So, you know, I want to map 1 maybe to -1. But definitely I'm mapping 1 to a negative number. I can't map 1 to any positive number anymore because we want it to be 1 to 1, right? So all the positive numbers are taken up, including 0. Well, 0 is not a positive number, but 0 is also taken up. So I definitely want some sort of negative n situation happening here. But this wouldn't quite work because if I just did negative n, this is what would happen. It'd be 1 to -1, 3 to -3, right? Yeah. So Caleb, you got what we're going for. You know, 5 to -5. That, you know, we're missing all of the even numbers here, right? So just like for the even numbers, let me repeat what I did for the even numbers. For the even numbers, right? The first, or okay, the 0th even number should map to the first positive, or okay, how do I explain this? So the 0th even number of n should map to the 0th positive number in Z. So I use the 0th here on purpose because 0 itself is not a positive number. So let's say the first even number maps to the first positive number in Z. The second even number maps to the second positive number in Z. The third even number maps to the third positive number in Z. So here, I want the first odd number to map to the first negative number in Z. Once again, the first odd number in n should map to the first negative number in Z. The second odd number in n should map to the second negative number in Z, right? So we have 1 to -1, 3 to -2, right? 5 to -3, 5 to -3, 7 to -4, and so on. And so what you're doing is, so 1 to -1, it's a little hard to see what's happening there. 7 to -4, what you're doing, right, is 7 to -4, right? Well, 7 over 2 is almost 4. First of all, I already said we were going to have a negative, right? We were going to make it negative, right? So 7 to 4. I already said that, you know, you definitely want to have some sort of negative n here, but -7 does not bring you to -4, right? -7 plus 1 over 2 does bring you to -4. So you see, we add 1 to it and divide by 2. Really just a little bit of pattern recognition here, right? So we put a negative in front definitely because we want to get a negative as an output. Then we want to add 1 to it and divide by 2, and that gets us -4. And let's see if that works for all of them. 5 plus 1 is 6. Make that negative, -6. Divide by 2 is -3, right? 5 to -3. And so that's what it is. That's the relation. It's negative n plus 1 over 2, if n is odd. But the real way to think about it, right, is this. For the even numbers, right? So let's just say nth. The nth even number of n should map to the nth positive number of Z, okay? And for the odd numbers, let's say for the odd numbers of n, okay, the nth odd number of n should map to the nth positive number nth negative number in Z. And this is the logic, and then 0 maps to 0. So there we go. That's kind of a better way of thinking about it. That's the logic of solving this problem, is to understand it like this. And then this is just sort of like, you just figure out the pattern to make that happen. So definitely a confusing question, right? Definitely a confusing question. I'd say this is definitely the hardest question from the practice work. So, you know, definitely I think this kind of question, just try to go over, if you're confused by it, right? Try to go over everything I've written here. See how I mapped what to what. See how I dealt with the even numbers and the odd numbers separately. And then from there, you know, try to go through, see how I made the formula and right? This is just an example of something relating to itself. Would it matter if it was flipped? So you want a bijection. Oh, first of all, sorry, before I answer, is it a bijection? Yes, it's 1-to-1, right? Because everything only gets mapped onto once, and it's onto because I'm getting all of these numbers. So there we go. Would it matter if it was flipped? So like n plus a half or n plus 1 over 2, probably you mean, n plus 1 over 2, and negative n over 2. So n plus 1 over 2 for even. So you're saying for even, n plus 1 over 2. So that would be, that wouldn't quite work, because if you have an even number and you're adding 1 to it, it's odd, so it doesn't divide by 2 anymore. And so you get a decimal. So that wouldn't work exactly what you're saying. But maybe if you meant other way around, negative n over 2, so even should be the upper bound. Yeah, even should be the upper. Okay, so but if you mean negative n over 2 and positive with this one, right? If you meant negative n over 2 here and positive with this one, then let's see if that works. So 0 would map to negative 0 over 2, which is fine. 2 would map to negative 2 over 2, which is negative 1. 4 would map to negative 2. Yep, that looks like it works. And then n plus 1 over 2 for the odd ones would make it even, divisible by 2, and the positive number. I think that works. Yeah, what you're saying. So this is it's not the same function, but it's another answer. I'm pretty sure. Could be, so I'll say or negative n over 2, n plus 1 over 2. If, for even and for odd. That's fine. That seems to work. Now you couldn't flip this up there, right? That would not work. Right. No problem, guys. Yeah, that is our time for today. It's 3:38. Okay, good. Happy that makes sense. That is our time for today. So hopefully you guys found this helpful. I will finish recording.